Okay. Okay, let me define one important concept, is a gradient. Gradient. Okay, gradient. Gradient is a vector. And this vector have important, super important property, two important property. Okay, suppose again, okay, we have z equal f(x, y). That's a function in two dimensions. And you compute the gradient. Gradient is this symbol, look. Gradient f is a vector. Okay, this letter is del. It's called delta. The gradient is, by definition, this is definition, a vector is a partial derivative with respect to x, comma, partial derivative with respect to y. It's a vector, and is the combination of the first component is partial derivative with respect to x, and the second component is partial derivative with respect to y. There's one important, super important property. I suppose you remember the lever curve. Lever curve. The lever curve is the curve that we obtain when you suppose that f of x, y is equal a number, k. And k vary, for example, 1, 2, 3, 4, 5, lever curve. And you obtain, for example, independent the surface, a family of the surface curve. Suppose something like that. Suppose that this is for 1, k equal 1, k equal 2, k equal 3, and so on, k equal 4. So now in one specific point here, suppose one point here, you have the tangent vector like that, boom. This is the vector, okay, you know how we compute that, is r prime to the specific point t, and the gradient vector is perpendicular to the tangent vector. The proof of this is relatively easy, because you suppose, for example, suppose, let me do quickly because I don't like the proof. Suppose that f of x, comma, y is equal a number constant in the lever curve. Now I define one lever curve using vector value function like that. And t is equal xt, comma, yt. So you are familiar with this concept. In 3 dimensions or in 2 dimensions, we can define curve using vector value function. Therefore, you can express this something like that, r like a vector t. So instead of x, y, you express it like that, x, y, like a vector value function. If you differentiate both sides with respect to time for t of this, it's obvious that the derivative constant is 0. And you apply here the chain rule. Because I know f dependent on x and y, and x dependent on t, and y dependent on t. So according to the chain rule in this derivative, we have derivative f with respect to x, okay, is this branch, multiplication, derivative x with respect to t, plus the second branch is this and this, derivative f with respect to y, time derivative y with respect to t, and this is equal to 0. If you express this equation like a vector dot product, look, you see this guy and this guy together is a gradient. Partial derivative f with respect to x, comma, partial derivative f with respect to y. Dot product, and this is this guy and this guy together is dx dt, comma, dy dt. And you know very well that when the one dot product, so this is the gradient, and this is the tangent vector, que es the velocity, ¿no? Entonces when you know que cuando one dot product is equal to 0 es because these vectors are orthogonal, 90 degrees. O sea, the gradient always is perpendicular to the tangent vector. Okay, entonces now you see this situation all the time. 90 degrees here. Okay, do you follow me? Everyone follow me? Okay, this is in 2D. Suppose in 3D, a little bit more complicated. One possibility, guy, is you suppose that the function is not like that. C is equal f of x comma y, and you express it like an implicit function, like that. F and x comma y comma z equal to 0. This is relatively easy, no? Because, for example, if you move the z to the other side, subtraction, well, you have that, something like that. So f x comma y minus z equals 0. And you consider in your mind that this is the capital F, implicit. Entonces, when you have implicit, or you manipulate in implicit form, and you compute the gradient in 3 dimensions, so the gradient of the capital F in 3 dimensions is, well, is a vector also, but in 3D, partial with respect to x, comma, partial with respect to y, comma, partial with respect to z. And this vector has exactly the same property of the 2 dimension, but in this case, no, with respect the level curves, the level surface. Entonces, level surface, a surface like that, the family of surface, because I try to represent one graphic is in 4 dimensions using 3 dimensions, apply the level surface. Entonces, when you compute the gradient is also a vector que es perpendicular, okay, gradient of the capital F is orthogonal, also the same idea, pero to the level surface. Entonces, this is a fantastic way to find the normal vector in any surface. You suppose, temporary, okay, this is a level curve. You compute the gradient in 3 dimensions, and this allows me, for example, find the equation for the tangent plane. Because the tangent plane, we need only one point, a normal vector. And a normal vector, I suppose, is the gradient. Evaluate in the specific point. This idea is clear or is confusing? Okay, so the most important that we study today is now the gradient. We can compute in 2 dimensions and 3 dimensions. The first property we study is the gradient is a vector that is perpendicular to the tangent vector in 2D, or is normal to the 3D. So normal to the level surface. Okay, that's it. No, we have more property important. Okay, I want to define. Today is the day of the definitions. Directional derivative. Oh, what is that? Directional derivative. Directional derivative is like a derivative in any direction. Entonces, according to the definition is, okay, the notation that we are using for directional derivative is like that. Look, D, capital D, UF. Evaluate in one specific point, A, B. Is equal. The same definition for the derivative, but in any direction. It's limited when the h approaches to 0 of the function. Evaluate in A plus h u1. I want to explain who is u1, comma B plus h u2, minus fn a comma b divided by h. The same definition of the derivative, but for example, when you're using partial derivative with respect the x, it's because u1 is 1 and u2 is 0. This is partial derivative with respect to x. Okay, of course, the notation that we are using, the most important notation is f of x. If, for example, u1, sorry, is 0 and u2 is 1, this is partial derivative with respect to y. But in general, we have that situation. Entonces, who is u? Well, u is a unit vector. So u is a unit vector, and the component for the unit vector is u1, u2. Okay, so what is the formula? Well, this is definition. The practical formula is the partial directional derivative, so derivative in any direction of the function f is equal the dot product between the gradient, dot product, the unit vector, and the direction in which you want to find the derivative. So I want to find the derivative in the direction que es defined by the unit vector que es u1, u2. One possibility to define direction is using unit vector. Another possibility to define direction is using angle. So I want to find in this specific point in that direction, okay, this direction maybe is suppose 45 degrees. Then you find the unit vector in this direction, no? Using the angle, the unit vector normally is cosine theta, and theta is 45 degrees in this case, comma sine theta. Okay, because you know the unit vector because cosine squared plus sine squared equal 1, square root this, the magnitude of this is 1. The magnitude of this is 1. So this is the fantastic formula to compute the directional derivative. You compute the gradient first. You have in your hand maybe the unit vector in the direction that you want to find the derivative, and you perform the dot product. It's important to understand gradient is a vector, unit vector is a vector. However, the derivative is no vector. The derivative is a scalar. It's a number, and this represents the real chain of the function in one specific direction. Okay, suppose que es 20. Okay, it's positive 20 or negative 20 is negative, decreasing. The same idea of the cal1, but now it's in multi-dimension. Entonces, using this new idea, super important property. This is the second property of the gradient. Okay, suppose the magnitude, okay, this formula is equal to say duf is equal magnitude gradient multiplication by magnitude u multiplication by cosine theta. You know the formula for the dot product, no? Is magnitude one vector multiplication by the magnitude second vector by cosine the angle in between both vectors. This is a classical formula that you are super familiar. However, unit vector, the magnitude is 1. So obviously this is equal magnitude of the gradient. This is 1. It's obvious it's 1 because it's unit vector cosine theta. Therefore, if you want to analyze in what direction the rate of change is maximum, I want to maximize this or minimize this. I can see, for example, si theta is equal to 0, es obvio que the directional derivative is equal to the magnitude of the gradient. Entonces es máximo. Okay, es máximo when you moving in the same direction of the gradient. So the gradient indicates us the maximum rate of change. I want to explain in detail this idea. However, minimum. Minimum is when the theta is equal 180 degrees pi. So the directional derivative is minus the gradient. Okay, so the conclusion is, for example, if you have surface and you want to find the steepest ascent, this surface is exactly that indicate in the same direction of gradient. Okay. So you want to do an opposite direction, steepest descent. So in what direction I go down faster is in the opposite direction. Of gradient. You want to find in another direction, well, we're using the formula for the directional derivative. Let me try to clarify this idea. Clarify. Any questions so far? Do you understand the idea or no? Okay. Let me recall. This is important. When I teach this, I realize that the student understand but don't get return the information. Okay, gradient is a vector. This vector indicate, so the arrow of this vector indicate the direction in which the function increasing faster. Okay, and the opposite direction is the direction in which the function is decreasing faster. Other direction, bueno, entonces decreasing or increasing depende si es positive or negative, the directional derivative. But the magnitude indicate how much decreasing or how much increasing the function. Okay, let me illustrate this one idea que I suppose que is very interesting. Suppose that we have a level curve like that. This is 5, 4, 3, 2, and 1. Why not? Yeah, I'm located here in that position. This is me. And this is the level curve of one surface. Okay, is, look, this mountain. Okay. Because I am in this moment, the point 1 is located here. This is the point 1. So say, for example, this level curve, one half. So as you travel, so you moving, you walking on this level curve, it's obvious you're walking in that direction around the mountain, no? This is the tangent vector. However, I know the professor explained me that the gradient vector is perpendicular always. Is 90 degrees to the tangent vector. This is the gradient. Indicate the direction in which you climb the mountain faster. Okay, so the gradient, I suppose, is in this direction. Okay. Bueno, okay. Entonces you move in this direction, no problema. And you get the second point, and so on. Okay. And so on. Okay, the gradient is always perpendicular to get the peak of the mountain. This is the idea, guys. Okay, not necessarily is a straight line. No, it's different trajectory to get this. But the trajectory is determined by the gradient. Okay, repetition. Gradient is a vector, have two important properties. The property number one is perpendicular to the level curve, or in other words, perpendicular to the tangent vector in a specific point, because we have another tangent vector maybe here. Look. Another tangent vector here, another tangent vector here, another tangent vector here. And also indicate the direction in what? In which you ascend faster with the maximum rate of change. Any question? Any question? Any question? Any question? Do you understand the idea or no? Come on, I want to hear opinion. It's important moment. Opinion. Charin, pretty good, pretty cool. Okay, pretty cool. Another opinion. Omar, all Richard is 110%. Okay. I try to do my best. Okay. Let me do an example. Super easy example. Suppose I have function f of x comma y is equal x times y at the point 2 comma 1 comma something. So this is x value, the point. This is a point P. 1 is a y value, and multiplication both is 2, no? So the point is 2 comma 1 comma 2, because this is z. C is equal f of x, no? Always. And the first question is find the direction of the steepest ascent at this point, at P. So we are in the point P, que es 2,1, and xy, no, and c is 2. So I want to find and why not inside the question 1, find the rate of change. Find the rate of change, numerical, direction and rate of change. And number 2 is find the direction to go increasing, of course, positive, at half this rate of change. So this rate of change we computed in the first question, no? Okay. Entonces, okay. Because I know that this word steep ascent indicate gradient. But the first thing I should do is compute the gradient. So the gradient is, by definition, partial the function with respect to x and partial the function with respect to y. This is the problem 2-dimensional. We can do it in 3-dimensional, but no. This is easier. And let's see another gets more convenience doing by 3-dimensional. It's 3-dimensional, but the gradient is 2-dimensional, 2 components. Okay, so the partial derivative of the function with respect to x, you take this function and you differentiate with respect to the x. Remember, guys, you consider when you differentiate with respect to x, you consider that the y is a constant and derivative x with respect to x is 1, so the answer is y. And f and y is equal x. Therefore, the gradient in our example and our function is y comma x. Wow, interchange x and y. And you evaluate in a specific point, que es 2,1, sorry, 2,1. X is 2, y es 1, entonces es the vector 1,2. Entonces we can determine direction, no? We can determine direction. Let me try to understand this. Do the graph. This is x, this is y. Well, this is the point, the vector 1,2. 1,2 is the vector like that. 1, 1, 1, 1 here, and the x component is 1, and 2 and the y component. This is the vector like that. This is the vector. In this direction, I guarantee you that the function xy, the original function is given at the beginning, is increasing with the maximum rate of change. Well, okay. Entonces, how you find direction? Well, you find direction in different way. You using unit vector, maybe, or find the angle. Let's do it in both ways. Suppose. To find the unit vector to indicate that direction, well, to say you take the gradient, you find the magnitude of the gradient, que es square root 1 square plus 2 square, radical phi, no? Radical phi. If you want to find unit vector and the direction can increase faster, is you divide our vector, gradient vector, divided by the magnitude is 1 over radical phi, comma 2 over radical phi. You can indicate in that way. So in this way is the unit vector, and the unit vector, remember, the information offer the unit vector's direction, because I know that the magnitude is 1. So in this direction defined by the unit vector, well, we have the maximum ascending steepest ascent. Entonces, what is the rate of change in that case? Well, the rate of change in this function is the magnitude of the gradient, que es radical phi. The radical phi represents, que is positive, of course, is ascent, the rate of change of the function in this direction. Okay, finish question 1. Find the direction using you. No, wait. Why no? Suppose another student que prefer define direction using angle. Okay, no problema. This is trigonometric. This is 1, this is 2. Entonces, the theta is equal tangent inverse 2 over 1, no? I put in the calculator, it's 63.43 degree. Okay, it's another possibility to express it. So in this point, I am in this point. However, if you moving in the direction 63.43 degree, you assume always that the 0 degree is on the x-axis. You moving on this surface with this rate of change, that by the way is the maximum. In the opposite direction is like that. Okay, it is 180 minus this, no? Is descending. Okay. Let's move on to the second question. Okay, number 2, find the direction que go increasing half this rate of change. Okay, half is 1/2. Entonces, the information is given is que the directional derivative of the function in this point, okay, by the way, is 2,1, is a half. Half is radical phi over 2, no? Radical phi over 2. Half of this. So when you move it in the same direction of the gradient, the rate of change is radical phi. I want to investigate now, when you're moving in other direction, I have no idea, the rate of change, the new rate of change is a half. Okay, so I know that this is the magnitude of the gradient, que es radical phi, cosine theta. It's obvious que cosine theta is 1/2. And this is theta equal, bueno, plus or minus pi over 3, 60 degree. 60 degree from this point. So when you move it in the direction 63.43, is maximum rate of change. If you moving in one direction like that, or in one direction like that, okay, 60 degree from this, 60 degree of minus 60 degree of this. The new radio chain is the half, is this. So we can express the angle like a 60 and 63.45, 43 point, this is 123 degree in this direction, or subtracting 63.43 minus 60, this is plus, this is minus, 3. Okay, it's super easy, super elementary, super straightforward. Any question, guys? Okay, well, let me show you. I planning to see this problem a little bit, because one image is much better than 1,000 words. I create one for this. Let me try to find. Okay, here, problem of the gradient. Okay, let me share the screen. Boom, 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 boom. Do you see the geometry right now? You see or no? Let's see. Okay, good, Ricardo. Okay, or you type. Okay. When we have a famous function is this. Look. By the way, what is the name of this function? What is the name? I insist in every lecture, because little by little you need to know the name of this function. What is the name of this? Okay. No idea. Look like hyperboloid, look like paraboloid, hyperbola. No, because es hyperbola, pero es solo su parábola, right? Entonces es hyperboloid parabolic. It's a combination. Look, this is, well, in this case, no, because it's rotating. And the extremity of that part, you can see the level curve. The level curve, and our famous point is the point 2,1. The gradient is this vector. I compare here. Is 1,2. And the angle of the vector is 63 point something. Entonces I indicate here one direction when there's 60 degree more. I don't know why I cannot do when it's minus 60 degree. So this is the disadvantage of GeoGebra when you have too much information. Entonces this is frozen. Or not frozen, sino que don't allow you typing more instruction. I don't know. I tried several times. I cannot. But this is the idea. Look at the point. This is the point in 3 dimensions. Look, it's our famous point A. Look at that. Look at that. Boom, boom. Here. You see the same point in 2 dimensions. That's B. Look at that. B. Because this is the x-axis, the y-axis, and the z-axis. You don't see because it's perpendicular to the plane. Okay. Okay. So you see, you rotate a little bit. Remember, x is a red one, y is the green one, and the famous point 2,1 here. This point A is exactly this point, A into D. Do you see that or no? No? Totally lost? Okay, we come back to the whiteboard. To bring easy and clarify example, no? Okay, so we're using gradient also to determine the tangent plane. Okay, again, tangent plane, important tangent plane. Tangent plane. And now, normal line. Wow, what is that? We have surface, for example. Then one specific point, I want to find a tangent plane. A tangent plane, guys, is a plane. It's a plane. It's a plane. One point. So if I try to see one view like that, you see the surface and you see the tangent plane here. Okay. A normal line. What is normal line? Well, a normal line is a line que passing through this point. But it's a line, no plane, and it's normal to the surface. Okay, let me use another color. Wait. Green. I use it for the normal line. Normal line look like that. Entonces, the equation for the tangent plane and the equation is easy. It's easy because we're using the gradient. My recommendation is the tangent plane and normal line, we're using the gradient, pero no en F, sino en capital F. So we're using the gradient like that. Gradient, capital F, is derivative x, comma, derivative y of the implicit derivative c. Now, you using this like a normal vector. This is our normal vector because I know the idea que this normal vector, when it's equal to the gradient, is perpendicular to the surface. Entonces we use a normal vector, the point is given, entonces you find the equation of the plane. Okay, when you evaluate the specific point, suppose que the point is a comma b comma f and a comma b, we find the equation for the tangent plane. The equation for the tangent plane is f of x minus a, plus f of y minus b, and plus f of c is equal z minus, f in a comma b. Equal 0, because it's like a dot product, no? So remember the equation for the tangent in vectorial way is a normal vector, dot product, r minus r null equal to 0. This is the equation for the any plane, with the information that we need. There's a normal vector that we have is a gradient, and the point is given, ABC. ABC, no, AB and C, is the C component, A normal vector is similar because the information that we need to define any line in 3D is direction vector and the point. Pero it's a coincidence que direction vector is a tangent, is a normal vector in the plane, no? It's a perfect coincidence. Entonces, the parametric equation x, y, x, y, z is the point A, B, and F in A, comma B, plus Fxt. So the number is, when you compute the partial derivative with respect to x, and you evaluate a specific point, you get the number. And the partial derivative with respect to z is a number, c, no, y, sorry, y. But the reason is y component. Yt plus the partial derivative with respect to ct. This is the formula for the normal line. Let's do in one example to illustrate the application for the one specific numerical example, tangent plane and normal line. Okay, good. Okay, suppose this example. Okay, suppose find the tangent plane a normal line of the surface. So find the tangent plane and normal line, okay, of the surface. expressed en implicit, ¿no? Entonces en implicit es, suppose f of x, y, z is equal, entonces you move everything equal to 0, this is implicit. Entonces en our example, f of x, y, z is equal x squared plus y squared plus c minus 9 equal to 0. Suppose que in one problem you have the equation expressed in implicit. Okay, no problema. Suppose que it's given in that way. X squared plus y squared is equal 9 minus c. So you moving this guy to the right hand side. Okay. And c you suppose is always f of x, y, pero little f, no capital. Okay, then you move everything to the left, right hand side should be 0, and this is implicit, and so you are ready to apply gradient in 3D. Okay. Entonces, question 1 is compute the gradient. Okay, number 1, compute the gradient. Wait, relax. I need the information for the original point. The point P is the point 1, 2, 4. Let me check in just in case, see everything is okay or no. Look. 1 is x. 1 square plus 2 square plus 4 minus 9 should be 0. This is 1, this is 4, this is 4. 4 plus 4 is 8, plus 1 is 9, and positive 9 minus 9 is 0. It's okay. These points belong perfectly to the surface. Entonces, I compute the gradient. The gradient, you compute the capital F of x, capital Y, and capital C. And you differentiate one by one. Derivative with respect the derivative this function with respect to x is just 2x, I suppose, no? But you consider que y and c is a constant, and derivative constant is 0. Likewise, when you differentiate with respect to y is 2y. And when you differentiate with respect to c, is 1. Because derivative c with respect to c is 1. Okay, entonces the vector, the gradient, sorry, is 2x, 2y, 1. Pero bueno, no. In the specific point, so the gradient in the specific point, we are working in the point 1, 2, 4. You evaluate plugging in, this is x value, this is y value, this is z value, pero the gradient do not depend on c. Entonces es obvio que es 2, because 1 here plugging in is 2, 2 times 2 is 4, and this is 1. This is my gradient in this specific point. And we're using the gradient to find the plane. This is, you consider que es normal plane. We're using the formula, no? The formula is, you take the component, this is, I suppose que this is the coefficiency of the plane. Remember, the plane is a x minus something plus b y minus something plus c c minus something equal to 0, no? There's one possibility to write this. And who is A, who is B, and who is C is this component, 2, 4, and 1. Entonces, 2x minus something, and something is the component, is 1 in the point. This is x null, y null, c null, in my example. Plus 4 times y minus 2 plus 1 time c minus 4 equal to 0. And the rest is super easy. You distribute the property, combine line term. This is elementary algebra. I skip that part. The answer is 2x plus 4y plus z equal 14. And this is the equation for the tangent plane. Express it, you know, like we are familiar in algebra. No? Is ax plus by plus c equal d. A is 2, B is 4, C is 1, and D is 14. Any question, guys? Easy or complicated? I'm feeling no. I need to find the second question, the normal line, ¿no? Pero the normal line is easy. The normal line parametric is x, y, z. And the point we are talking about is this point 1, 2, 4. 1, 2, 4. And the direction vector is exactly coincident with the normal vector for the plane. It's 2, 4, and 1. Entonces 2t. 4t. And 1t. Wow. This is the equation for the normal line. Normal line. And t, you know, t is from negative infinity to positive infinity because it's a line extending in both directions. Any question? Let me try to find one script I use in GeoGebra. Let me try to find, guys. I have some delay to find this. Oh, I found. Okay, good. Saving, loading. There you go. Boom. Okay, no. And no. And no. Okay, let me share with you the GeoGebra script I create to illustrate tangent plane and normal line. Switching to this. Do you see that? Okay, super. This is the same example. It's a paraboloid. Look at that. This is our famous paraboloid. And this paraboloid open down because it's and the z intercept point is 9. 9 minus x squared minus y squared. You identify que es paraboloid because x and y is raised to the second power. C no, C is 1 power. Entonces paraboloid. In what direction? Open down because the x is, so the term square is negative, no? Entonces down. The parabola is open down. Let me plot the point. Boom. The famous point. Boom. Look at the black color. The point is the point 1, 2, 4. Good. Okay. So I want to investigate the tangent plane in this point. Boom, 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 boom. Look. The equation that we found, 2x plus 4y plus c equal 14. Bang. Look at that. It's a tangent plane. Do you see the tangent plane? Okay. And finally, okay, he do so very well. And the normal line, whoa, look at that. It's a line, look, it's a normal line of our surface. Okay, I like that. I have another example, more complicated, a little bit more complicated. Let me try. Okay. Let me come back again to the whiteboard. Okay. Erase the board. Okay. Everyone follow me, guys? Everyone follow me? Do you understand very well? Okay. Remember, I suppose you start doing now the homework 5, 6, 7, and 8. Okay. Any question you have about homework? You know what is my schedule in the lab, like a tutor. I work in Monday, Thursday, and Friday. Tomorrow, not today. It's a 1 to 5 p.m. This is 4 to 8 p.m. And this is 1 to 5 p.m. So today, from 1 to 5 I am, and also we have another tutor can help us in this subject, no? Guys, I know you have your friend can know mathematics. Okay. Anyway, you are smart and but you need to complete it. See you. Okay, it's important you understand. See you take good grade in the reading test, and you get ridiculous grade in the online. You don't pass because it's 50 approximately. I consider extra point in the homework I consider a extra point in the subscription in the YouTube channel. Okay. Anyway. Okay. Let's study another thing. Another example gets related for this. For example, you find another problem similar. You find the parametric equation of the tangent line. Oh, now it's tangent, no normal. Tangent line to the intersection to the curve intersection of intersection this is S of Z equal x squared plus y squared and 3x squared plus 2y squared plus z squared. Wow, what the hell? Equal 9. I need to know the name of this guy. I need to know the name of this surface. Okay, you know, very well know. Come on, name. Professor, I can see the... Okay. Let me try again. Share whiteboard. It's okay? Do you see, mister? Do you see or no? Yes or no? Answer me. Help me. Not yet. Okay, let me try. I discovered that sometimes I need to stop sharing and switch into a specific window. Okay. Now, everything okay? Good. Restrepo. Okay, what is the problem that we have, Restrepo? When we have two surfaces like that, I have no idea. In general, one surface, and we have another surface. And this surface intersect, form a curve. Ow. Form a curve. Entonces, en one specific point, okay, by the way, it's given. Sorry, I forgot to write that. At the point, at the point 1, 1, 2. Okay, if you plug in this point in the two surface, I suppose it matches perfectly, you know? You need to find the tangent line. The tangent line. Tangent line is a line like that. Find the equation for the tangent line. So what is the idea? When we have one surface, this surface, okay, I want to express it in implicit. You put capital F, x comma y, comma c equal to 0. And likewise, this is another surface. I want to go capital G, x comma y, comma 0. I express it both in implicit form. Yeah, I find the gradient. I find the gradient both. I find the gradient in capital F and the gradient in capital G. Okay, entonces in this specific point, I know that the gradient is perpendicular to the level surface. So the gradient F look like that, and the gradient G look like that. This is gradient of F, and this is gradient of G. Okay, and remember, our goal is find the tangent line. So our goal is find the line, and the line we need direction vector. Okay. The direction vector, I suppose, okay, something like that. Okay, and this is perpendicular to the both gradient. So what's the idea? You compute the gradient for the first level surface, you compute the gradient for the second gradient surface, you perform the cross product, and you find the direction vector. Okay, we need direction vector and the point. Wow, it's super easy to find the equation for the tangent line. Okay, let's do it. Do you understand this tragedy or no? Okay, we have two surfaces. This surface intersecting. I have the GeoGebra can illustrate very well this idea. Okay, but nobody explain me what is the name of this surface. Nobody explain me what is the name of this surface. What is the name? First name, last name. Circular paraboloid. Good, Giraldo. This one. Circular paraboloid. This one. Circular. And this one. No, no idea. When everything is a square and it's completed. You can, for example, divide by 9. Es elipsoide. Es obvio que es elipsoide. Okay. The only student que remember very well the surface is Giraldo. Wow. Okay, let's do it. I take the first equation, que es z equal x squared plus y squared. I copy in implicit. I move everything to the left or to the right, doesn't matter. Entonces x squared plus y squared and minus c equals 0. Okay, super. I move to the left, to the right. You put it in an elegant way that you prefer. And bueno, this is my capital F function. Capital F in x comma y comma c is equal that function. This expression. I compute the gradient. Gradient capital F is derivative with respect to x. It's 2x. It's easy. Look, derivatives. Comma. With respect to y. It's 2y. With respect to c is negative 1. And you evaluate at the specific point. So the gradient, this is the general gradient, no, of this surface. But in a specific point, okay, the gradient is the S1, S2, 2, because x and y, look, x and y is 1. And c is 2, but I don't care because the gradient do not depend on c is negative 1. This is my first vector. This vector. No, sorry, this vector. This vector. Likewise, very, very similar. Let's do it in the G surface. In the G surface, expressed and implicit is g x comma y comma z equal to 0 is equal to 3x squared plus 2y squared plus c squared minus 9 equal to 0. And the gradient is partial derivative with respect to x. Here is 6x, comma. Partial derivative with respect to y is 4y. Partial derivative with respect to z is 2z. And you evaluate in the specific point. Okay, it's the point 1, 1, 2. Entonces 6, 4, and 2 times 2 is 4. Okay, I have this vector. Now perform a cross product. Doesn't matter what you are doing first or secondly, because the only thing that change is the direction. Pero no, I prefer in that order. Cross product F gradient cross product G. Entonces sí es I, JK, the standard orthonormal unit vector. You copy 2 2, -1, and 6, 4, 4. Okay, so I want to skip the tedious cross product. Okay, you know very well. And the answer is 12, -14, and positive -4, sorry. Okay, you can leave it like that. However, remember, I need direction. I need direction to say if you can see, for example, divided by 2 is the vector 6, -7, and -2. And this vector is exactly the same direction of this. It's shorter, but I don't care because the only information I need to find the line is the direction vector. Entonces, it doesn't matter if this vector is unit vector or no. The magnitude is not important. The important is the direction. Okay. Entonces now my equation for the tangent, no? Tangent line is x, y, z in parametric. The specific point is 1, 1, 2, 1, 1, 2. Where I come from this? Look here. And the direction vector is this. Is 60 minus 7t and minus 2t. Suppose that you don't realize this idea division by 2. Suppose it's not important. You put 12 here, you put -14 here, and -4 is the same line because the t is arbitrary number from -infinity to positive infinity. So this multiplier is not important. It's totally irrelevant. Sure or no? Super. Okay, let me show you the script of the algebra I prepared for this problem. Let me try to find. Okay. Let me try to find. Okay. There you go. I found. Okay. Let me try. Boom. Do you see? Okay. Let me try to analyze step by step. Okay. Yes. Here I am. Okay. Vectors. Okay. Two. Okay. We have two surfaces. Look. We have the paraboloid, in this case open up, and we have the ellipsoid. Boom. Entonces this surface intersecting in one weird curve. To find the equation for this curve is very, very complicated. Well, I don't care. This is not my problem now. Okay, my problem now is I have a point, que es the point, famous point 1, 1, 2. Entonces, in this point, I found different vector. Okay, this vector is the gradient of the ellipsoid. Okay, que es perpendicular. Look, you see que es perpendicular? You see que es perpendicular or no? I'm confused. Of course it's perpendicular. Oh, of course perpendicular. It's the gradient of the ellipsoid. Okay, so now the paraboloid. And this is the gradient, let me see, of the paraboloid, I suppose. Wow, it's too large. No. Okay, this one. Okay, this one is the gradient of the paraboloid. Let me see if it's true or not. To understand this, I remove the ellipsoid. Let me see, ellipsoid. No, I don't like ellipsoid now. I don't like this vector now. Okay, look at that. This is normal vector of the paraboloid specific point. Okay, restore ellipsoid, restore the gradient for the ellipsoid, Now. Let me see. Well, this is dot product B. And this is the dot product. Boom. Wow. Dot product is a big vector. I don't care. Now, the equation of the tangent line is this. Boom. And blue color. Okay. Tangent line is a line que touch both surfaces in the same common point. It touch in only one point. That is the reason it's tangent line. Everything is clear? Wow, amazing. I like that. Okay, let me switch into another topic. Important topic. Okay, important. Let me come back to the whiteboard. Whiteboard now, share. Whiteboard. Erase everything. Okay. Let me try to explain now another thing, another application for the tangent plane in engineer. Look, total differential. We don't use this in Cal 1. It's possible to find, but no, we use in Cal 1. Okay, let me copy one more time the equation for the tangent plane. The equation for the tangent plane is fnx comma y is approximately, remember, is the function x comma y is approximately to the linear approximation, que es the tangent plane. Okay, and this is equal the function evaluating one specific point, a comma b, plus a partial derivative with respect to x evaluating a comma b, x minus a, plus partial derivative with respect to y evaluating the specific point, so this is numerical, y minus b. Okay, entonces the interpretation, this guy, and this guy is similar, is z. This is C null in a specific point. This is partial derivative. Let me copy in this notation. And this, I suppose, is delta x. It's the difference between the x. And this is the partial derivative with respect to y. And this is delta y. This is delta x. And this is delta y. And delta y. Okay, si I move this z0 es c minus z0, que I suppose que es delta z. Okay, entonces my equation total differential is, okay, so you transform this delta to differential, because you assume que es equal dc is equal partial the f with respect to x, dx plus partial f with respect to y dx. Okay, it's a formula for the total differential, and this formula we can apply for any dimension, for 2 dimension, 3 dimension, 4 dimension, 20 dimension, because depending. So we using in general, for example, you have a formula. In engineering you have formula, and you need to compute something, and you have the error in the dimension. So what's the problem I want to discuss now? The problem is you have one problem in which you need to find something, but in the real life we have error in the different dimension. I need to investigate the propagation of the different variable error inside the total error and the original function. Okay, entonces, for example, suppose que we have more complicated. We have w depending of x, y, z. Okay, entonces the formula for the total differential, in this case we have 4-dimension problem, no, is dw is equal partial the f with respect to x times delta x or dx, differential, plus partial the f with respect to y times dy plus partial the f with respect to z dz. In this case you have function que the independent variable is w, I don't know what is that, and dependent of the 1, 2, and 3 independent variables. So see, now it's not dependent, it's independent. Okay, to understand much better this, I put the elementary example, and you see very well, very clear this idea of this and the application of this. Suppose that we have a box. And the actual dimension for the box, okay, this is the length, I, capital L, is 80 centimeter. We have W, get the dimension, W, width is 60 centimeter. And the height is 50 centimeter. However, this dimension is measured with a specific error. Entonces, the error is using the same instrument, the same tools, and delta L, que es the error, is 0.2. 0.2 or 0.1? 0.1. 0.1. I don't know, remember si es 0.2 or 0.1. Bueno, I suppose que es 0.1. 0.1 centimeter. Delta W is equal 0.1 centimeter. And delta H is 0.1 centimeter. The reason is the same is because we're using the same rule or the same instrument to measure the dimension. Entonces now the error is common, it's the same. Entonces now I want to find, for example, I know que the surface area, suppose the material que we go through this box, suppose que es, I don't know, suppose que es aluminum. Okay. Surface area formula is 2 times LW because we have two faces, plus 2 times L times H, plus 2 times W and H. I suppose that we have totally compact box, no open in any face. Entonces I need to find that, but this is super easy. It's multiplication. That's it. The multiplication by 2, no? And addition, no? However, I need to find delta A. So what is the propagation of the error? Okay, when you introduce this error in this quantity, this error in this quantity, and this error in this quantity. Okay, we can do that without calculus. In this case, it's relatively easy doing without calculus because you define minimum maximum, no? So that you see the L is plus or minus delta L, and you addition delta L and subtraction delta L. You can do in any quantity, and you take the maximum and the minimum, and that's it. It's super easy. But I want to illustrate using calculus book is maybe in another more complicated problem in which you have more complicated function. So it's complicated doing that way, and you take advantage the linear approximation, and you take advantage the formula for the total differential. Okay, entonces we have one independent variable que es A, capital A, que es surface area. Surface area. The yellow part. Entonces this is a function que depende, this function capital A, es a function que depende of L, W, H. Three variables, three independent variables. Okay, entonces we're using this. To find delta A, You compute partial derivative A with respect to, for example, L times delta L plus partial derivative area with respect to W multiplication delta W plus partial derivative area with respect high multiplication by delta H. Okay, let's compare the partial derivative independent, no? Okay, to make easier the problem, let's say partial derivative A with respect to L, partial derivative A with respect to W, partial derivative A with respect to H. I copy the formula. Our formula is A is equal to LW plus 2LH plus 2WH, no? Doesn't matter the order. So when you compute the partial derivative with respect to L, you consider the L here and here. Entonces 2W es obvio. You consider que the rest is constant. Es 2W plus 2H. Make sense? Everyone follow me? The partial derivative with respect to... Bueno, actually you can see que 2 es a common factor. Entonces W plus H. Entonces el partial derivative A with respect to W is 2L plus 2H, ¿no? Es 2L plus H. Because W here and here. Okay, good. And partial derivative A with respect to H is 2L plus 2W. The formula is 2L plus W. Super. Well, the only thing you should do is plugging in where? In this formula, no? To compute the error. How is the propagation for the error in this problem? Well, is okay, delta A. Okay, delta. Okay, in this case, simplification, this number, and this number is the same, at 0.1. At 0.1. And 0.1, okay, multiplication by 2, okay, you have 2 in any expression, at 0.2. So delta A is equal to 0.2. Where come from 0.2? Well, 0.1 times 2, no? So now multiplication what? Multiplication no. Addition, no? No, es addition. O sea, es addition. Es 60 plus 50. Es 100. Okay, it's 110. Where come from that? The dimension at the beginning was L equal 80. W is equal 60 and H is equal 50, ¿no? Centimeter. Entonces I did that part, W que es 60 and 50 is 100 plus 130. Sorry, no paréntesis, no close the parenthesis, I don't finish. Plus 140, ¿no? 140 is this plus this. So when you multiplication this time 0.2, let me try to do rectification in my calculator. Well, I did in my paper, but I don't know sure that I'm doing good on 110 plus 130 plus 140. Multiplication by 0.2 is 76. And the unit of this is obvious is centimeter square. This is the error. And the area, no, the area is super easy. The area is 2 times multiplication 80 times 60 plus 80 times 50 plus 60 times 50, no? And that is 23,600 centimeters. This is the material that we need to use, but plus or minus this is the error. And the answer is 23,600 centimeters plus or minus 76 centimeters. This is a straightforward example. Maybe in the real life, when you are doing engineer and you need to build something, no? Entonces now I have a formula, a state relationship between the error and what is the propagation of the error. This is common in physics. It's also using this. Okay, guys, I want to spend the rest of the time in one theoretical part because I need to complete your knowledge about. Okay. Look. Any question about the differential, total differential formula and its application and compute the error propagation? No? Everything okay? Okay. Entonces, the thing, okay, good, all good, okay. The thing that fly in the air, por ejemplo, esto de en Cal 1, esto de en Cal 1, en Cal 1 hay esto de continuity. Que es when the limit of the function, Cal 1 single variable, only one, is equal to the function evaluation. So basically, this formula implies three things. Number one, exists the limit. Number two, exists the function inside the domain. And number three, both are the same. This is continuity. And differentiability, differentiability is more sophisticated concept like a continuity because we have more condition that limit exists. Exists this limit. And sometimes this limit fail. How fail? Well, suppose that the function is continuity. Pero continuity like that. We have this kind of point, okay? Is a corner or cup. In this case, the derivative failed because you find the derivative a little bit to the left is one slope of the tangent line is 2, and the limit must be unique. Okay, this is differential. This is Cal 1. This is clear. So, okay, in elementary word, without mathematics, how you define I? How you define erase? Okay, no canvas, sino erase specific last sketch. Okay, good. Okay, continuity. So one function is continuous when you can drop the graph without lifting the pencil from the paper like that. Ooh. And it's also continuous, but not differential. With differential, it's a smooth curve without corner like that, without sharper points, without cup, without gap, without hole. Well, a hole is okay. Now let's move on to the Cal 3. This is Cal 1. In Cal 3, the situation is a little bit confusing for me. It's because we study continuity. Okay. Continuity we study. I suppose that you understand. Limit when the x comma y approaches to one specific point, a comma b, of the function in 3D, for example, is equal a number, pero es a number coincidente perfectly with the function. It's a continuity. We study partial derivative. But the partial derivative is very limited concept because it's the derivative in a specific direction. Now the thing I try to discuss it quickly, of course, because is differentiability. Differentiability is que existe the derivative, pero in any direction. So again, the stupid thing, I need to prove in infinity direction. No. No, no, no. What is the idea? What is the idea? The idea is, look, okay. We have, for example, we have the function. And the function, you can estimate like a linear approximation. Okay, by the way, the linear approximation is the tangent plane plus error. Okay, this error depending x, y. No? If you will be able to prove that when you approach it to the point, so when you approach it, how you approach it like that, limited. When the x comma y approach it to the one specific point I want to analyze a comma b. And the error, this error, okay, its error was the differences. Here you subtracting the original function minus the linear approximation, que es the tangent plane, guys. It's the tangent plane. Okay, you find the tangent plane, you have the function, subtraction, this is the error expression, divided by the distance, que the distance is x minus a squared to any point for the specific point, plus y minus b squared. See, when you compute this limit, the answer is exceeds the limit. Exceeds the limit. Exceeds the limit. And it's equal to 0. Wow! Entonces the function is differential. Okay, this is very, very complicated doing algebraically. You know, guys, que the limit is crazy. The limit in multivariable is crazy. But the thing I try to explain is that if, for example, the partial derivative exists, and this is not enough condition to the function is differential. So I try to put here one idea. Look, illustrate a little bit. I don't know if it's good or not. The idea for the differentiable, continuous, and partial derivative. It's totally different concept. Okay, this is exist partial derivative. This is differentiable. This is continuous. And this is the collection of any derivative in any direction. O sea, the function has a partial derivative, pero no partial, sino derivative in every direction that exists. It's a exists derivative in any direction. And how you prove this direction? Because you consider no direction, you consider a tangent plane. And the tangent plane and the function, the error decreasing. Okay, entonces si you will be able to prove, pero using this new idea, que the derivative in any direction using tangent plane exists, entonces now imply que es differential. Okay, and the traditional way is this. Si es differentiable, es obvio que es continuo. And si es differentiable, es obvio que the partial derivative exists. Remember, this is a subset of this big, strong concept. Que es in any direction. In any direction, you condense it like a tangent plane. Another direction, completely crazy. Doesn't work. For example, si the function is continuous, it's not necessarily differential. This is Cal 1. This is Cal 1. Okay. Si the function is the partial derivative exists, not necessarily is differential. There are many counter examples to illustrate this idea. No. In this direction, it's obvious que no in both directions. No, not necessarily continuous. There are no relationship between continuous and partial derivative. Entonces, what is the thing, professor? One of the thing is to prove differentiable, you need to prove that we have exist the derivative in any direction, and you prove this using this idea. I know that it looks like complicated. Actually, it's complicated. It's theoretical complicated. But this, I need you know this new idea. Okay. The most important thing that you need to understand that the partial derivative is a weak thing to explain differential. So we need to prove in infinity direction. How you prove? Using tangent plane and using this equation of the error. Okay, too much, guys. Let me check it out. How the I grade the test 1. I see that some student forgot. I suppose they forgot because it's good students.